Welcome to The Explainer. Today, we're zooming way in to look at the invisible chemistry that literally shapes our material world. We're going to break down the elements into opposing factions, watch how they clash, and see exactly how human ingenuity has hacked them to build modern civilization. Let's dive right in. Think about this for a second. Why does a standard iron nail rust away into dust, but a gold coin can just sit there submerged at the bottom of the ocean for centuries, completely unchanged? Seriously, zero difference. The answer to that mystery is all about the hidden elemental dynamics happening right at the atomic level. And to understand that, we first need to figure out who the players on the board actually are. So, let's meet the elements, the factions of our material world. When you look at the grand periodic table, elements basically fall into two opposing camps. First, you've got the metals. These are the heavy lifters, right? They're lustrous, they're shiny, they're malleable, meaning you can hammer them into flat sheets, and ductile, so you can draw them out into wires. Strike them, and they ring. They're hard solids, and they are fantastic conductors of both heat and electricity. On the flip side, we have the nonmetals, which are pretty much the exact opposite. They're usually dull, they're brittle if they happen to be solid at all, and honestly, they're terrible conductors. It is a really stark dichotomy. But, chemistry loves to throw a curveball. The rules aren't absolute. Take mercury. It's a metal, sure, but it's a liquid at room temperature. Or look at sodium and potassium. They're technically metals, but they are so soft you can literally slice them with a butter knife. And then the nonmetals have their own rule breakers. Carbon gives us diamond, the hardest natural substance known to man, and graphite, a nonmetal that actually conducts electricity. So yeah, expect exceptions.
Which brings us to the rules of reactivity, or what I like to call chemical combat.
Normally, when metals react with oxygen, they form metal oxides that are strictly basic. Copper and oxygen make copper oxide, pretty straightforward. But then you have these chemical double agents known as amphoteric oxides. Elements like aluminum and zinc don't just pick one side. Their oxides uniquely react with both acids and bases to produce salt and water. They are highly adaptable when things get volatile. So who actually wins in a chemical fight? Well, that's dictated by the reactivity series. Think of it as a strict VIP hierarchy. At the very top, you have the highly reactive heavyweights, potassium, sodium, calcium. They will violently displace other elements. In the middle, the moderately reactive tier, like zinc and iron, a bit calmer, but definitely still prone to chemical changes. And at the absolute bottom, copper, silver, and gold. Because they're the least reactive, they essentially just ignore their environment, which, going back to our earlier question, is exactly why gold makes such great, long-lasting jewelry.
To put this hierarchy into perspective, imagine dropping top-tier sodium into cold water. It doesn't just dissolve, it violently tears the water molecules apart, releasing hydrogen gas and a massive amount of heat. It's explosive. But drop bottom-tier gold into boiling hot water or steam? Absolutely nothing happens. Total indifference. Now let's talk about the atomic handshake, transferring electrons. So how do these rival factions actually team up to form compounds? It's all about the electron exchange. Metals have this strong urge to shed electrons, which turns them into positive ions. Nonmetals, on the other hand, are desperate to gain electrons, making them negative. When sodium meets chlorine, they do this microscopic atomic handshake. Sodium just hands its electron over to chlorine, and boom, you get an electrovalent or ionic compound, in this case, perfectly edible table salt. Because those positive and negative ions are intensely attracted to each other, ionic compounds share some very specific traits. They form solid, hard, brittle crystals. You need massive amounts of heat to break them apart. And here's a really cool quirk. As solid crystals, they don't conduct electricity at all. But if you dissolve them in water or melt them down, freeing up those charged ions to move around, suddenly they become fantastic electrical conductors. Moving on to extracting the hidden metals, going from dirt to shine. Let's get our jargon straight before we start digging. In the Earth's crust, we have minerals, which are naturally occurring elements or compounds. But what we actually want are ores. These are specific minerals where extracting the metal is actually profitable. Of course, ores aren't pure. They're mixed with gangue, which is just a fantastic word for all the useless soils, sand, and rock we have to strip away. For moderately reactive metals like zinc or iron, extraction is a multi-step journey. First, identify and mine the ore. Second, you have to bake it into an oxide. You either roast it in excess air if it's a sulfide, or use calcination with limited air for carbonates. Third, you bring in carbon.
The carbon basically acts like a thief, stealing the oxygen and leaving us with a reduced metal. But even then, it's not quite pure enough for modern manufacturing. That's where the crucial final step comes in: electrolytic refining. We drop the impure metal into an electrolyte bath. Once we run a specific electrical current through it, something almost magical happens. The pure metal atoms literally dissolve off the impure block, swim across the liquid, and perfectly deposit themselves onto a pure strip. All that leftover dirt and gangue, it just falls to the bottom as anode mud. And there you have it, perfectly pure metal. But here's the great irony of it all. After all that incredible effort to extract and purify these metals, why do they almost immediately start trying to destroy themselves? That brings us to fighting corrosion with alloys, the battle against rust. We call this slow destruction corrosion. You see, nature actually prefers elements in their oxidized states, so the environment immediately goes on the attack. That tarnished silverware in your drawer, it's turning black because it's reacting with air to form silver sulfide. Copper reacts to form a green basic copper carbonate, which is exactly why the Statue of Liberty is green. And then there's iron. Exposed to air and water, it inevitably turns into flaky reddish-brown rust, literally eating away at our infrastructure. Since rusting iron is a massive vulnerability, human engineering had to get clever. Sure, we can paint it or oil it, but one of the absolute best defenses we have is galvanization. By coating iron in a layer of zinc, we're basically hacking the reactivity series. Since zinc is more reactive, it takes the hit. It sacrifices itself to the environment, keeping the vital iron structure underneath completely safe.
But honestly, why just coat a metal when you can rewrite its DNA? Enter alloys. By mixing a metal with other elements, we can drastically upgrade its superpowers. Mix copper and zinc, you get brass, way stronger. Mix copper and tin, you get bronze. Throw some nickel and chromium into iron, and you get stainless steel. It practically solves the rust problem altogether and gives us the sheer strength needed to build the modern world.
So, we've traced the whole journey, from the raw elemental factions, through their chemical combat, all the way to how human ingenuity extracts and upgrades them. But it leaves you wondering, if we can manipulate violently reactive elements to conquer rust and build soaring skyscrapers, what impossible material are we going to invent next? Keep questioning and pay attention to the elemental dynamics happening all around you every single day.